about the distribution of a correlation coefficient? So the correlation coefficient again ranges from a value of -1 to +1. 0 means that two variables are uncorrelated. +1 is perfect positive correlation. -1 is perfect inverse correlation. Everything in between is some level of correlation. And we have the picture here shows that we have a very weak correlation between vitamin D and cognitive scores. So what's the distribution of a correlation coefficient? Another measure we can calculate from our data. Let me do another computer simulation. So in this computer simulation, I said that the true correlation between vitamin D and cognitive function in the entire population of older European men is 0.15. If that's true, then I can sample from that population, sample both vitamin D levels and cognitive scores. I select a random sample of 100 virtual men. They all have a cognitive score and a vitamin D level based on this underlying correlation. I calculate the correlation coefficient in the sample. And then I do this again and again and again, and let's say I do it 15,000 times this time. You're getting the idea of a computer simulation now. And then we can explore the distribution of those 15,000 correlation coefficients. So here it is. Here's the results. So notice, it's on a normal curve again. Well, this is great. Lots of statistics follow normal curves. So it turns out that the normal curve is very important for this reason. So here's some things. It's normally distributed, hooray. The mean turns out to be exactly the true correlation, 0.15, because most of my samples come out somewhere around 0.15. I asked the computer to calculate the standard deviation of these 15,000 observations, what we would also call a standard error here. It came out to be, in my simulation, 0.10. So that's, from my computer simulation, the distribution of the correlation coefficient. It turns out that the shape of the distribution for a correlation coefficient, as with the mean, it's a normal distribution as long as we're talking about sample sizes above 100. It is on a t-distribution, though, for smaller samples. So if you have smaller samples, there's some additional uncertainty, and you actually are on a t-distribution, which looks a little bit different. So for smaller samples, you have to worry about being on a t rather than a normal. But for larger, as in this example, it's essentially on a normal. The mean of the distribution of a correlation coefficient is the true correlation coefficient, not surprisingly. The standard error somebody's worked out with mathematical theory. It turns out to be approximately the square root of 1 minus r squared, and r is the true correlation coefficient in the whole population, divided by the square root of n. Notice it has a lot of similarity to the standard error of the mean. They both have square root of n in their denominator. So bigger samples mean smaller standard errors once again. Turns out that many statistics follow either normal distributions or, for small samples, t-distributions. So this is great. You saw two examples already. It popped up to be a normal distribution even when we didn't start on a normal distribution. It turns out lots of statistics follow normal distributions or t-distributions. So statistics that follow t-distributions for small samples and normal distributions for large samples include means, as well as difference in means, and correlation coefficients, things we just saw. Things that follow normal distributions, whether or not you have a small or large n, that is, it's always on a normal distribution, include proportions, risks, differences in proportions, and a statistic that has to do with the odds ratio. And since we spent a lot of time on the odds ratio in week 2, I thought I'd just introduce this now. It's not quite the odds ratio that follows a normal distribution. It's the natural log of the odds ratio that follows a normal distribution. So let me just end with this last statistic, the odds ratio. What's the distribution of an odds ratio? Let's do another computer simulation. You can see how much I love computer simulation. So let's do a simulation for an odds ratio to figure out the distribution of an odds ratio. So I'm going to say I'm going to be doing case control studies. So there'd be a reason to calculate odds ratios as I'm doing a case control study. I'm going to tell the computer, imagine I've got this large population of cases and controls. And 20% of cases are smokers and 20% of controls are smokers. I want to know that I would be doing a case control study here to gauge the relationship between smoking and being a case. And let's say that there actually is no relationship. The odds ratio here happens to be 1 because there's equal amount of smoking in both groups. That's my underlying population, and then I'm going to do my simulation. So I'm going to repeat over and over again case control studies with 100 people, 50 cases and 50 controls. Every case and every control has a 20% chance of being a smoker. In other words, it follows a binomial. So that's how I can do this in a computer. I can tell the computer that we're on a binomial. So I randomly select 50 cases and 50 controls. For that one sample, I calculate an odds ratio, I store that in a data set, and then I do this again and again and again, like I'm doing repeated case control samples, repeated case control studies with different samples of the same size. Repeat it, say 1,000 times, and then I'm going to observe the distribution of the odds ratio. So here we go. Here's what it comes out to look like. Ah, wait a minute. Oh no, it's not on a normal curve. Oh dear, everything else came out on a normal curve. The odds ratio doesn't naturally follow a normal curve. It doesn't follow a bell curve. So notice that the distribution of the odds ratio has a right skew. The true odds ratio was 1.0 here, so we are centered around 1.0, but we have this right skew. Why would that be? Well, the odds ratio is a little different than the other statistics we've talked about so far. The odds ratio is a ratio. Ratios cannot have values below 0. So we have this right-hand boundary. We can't go below 0. So we kind of end up clustering and going right up into 0, but we can't go over it. On the other hand, an odds ratio can be as big as you please. We've seen some big odds ratios in this class. So the odds ratio can go way out. It has no bound on the right-hand side. So you can end up with, even when the true odds ratio is 1, you can end up in a given sample, when you have small samples like this, you can end up with some pretty big odds ratios. Notice that 1 in 1,000 times, even though the true odds ratio here is 1, that means there's no association here, just by chance, 1 in 1,000 times we got an odds ratio way, way out here at 6.8. So it can happen just by chance, but it's a right skewed distribution. So that's a problem because we want everything to end up on a normal or a t. So what can we do to force this to go onto a normal curve? Actually, there's a little transformation we can make that will turn the odds ratio, the distribution of the odds ratio, into a normal curve. What we can do is just simply take the natural log of the odds ratio. Here's the histogram when I take the natural log of the odds ratio. Yay, we're back on a normal curve. So what happens is that when you take the natural log, any value for the odds ratio that's between 0 and 1, that's a decimal. When you take the natural log of a decimal, you end up with negative values. So you bring back the negative values back into play, and now you end up on a beautiful normal curve. It's centered around 0 because the natural log of 1, which was the true value here, the natural log of 1 is 0. So this curve ends up centered around 0. So we're back on a normal curve. So even when we don't start on a normal curve naturally, we can force statistics to be on a normal curve. And when we do statistical inference on odds ratios, we actually are always working with the natural log of the odds ratio for this reason. Now, somebody worked out from mathematical theory the standard error of the natural log of the odds ratio. So this is the standard error for the natural log of the odds ratio for this curve here. And it turns out to be the square root of 1 over a plus 1 over b plus 1 over c plus 1 over d. Don't worry about that formula, but just realize that, well, a is exposed cases, b is exposed controls, c is unexposed cases, and d is unexposed controls. In other words, these are the sample sizes. These are just the sample sizes of particular groups, but those are the sample sizes. And notice that the smallest of those group is contributing the most to the standard error because it's reciprocals we're looking at here. So that's the standard error of the odds ratio, the natural log of the odds ratio. Notice that, like the other standard errors, sample size is very important, and sample size is in the denominator. So let me just summarize this. The distribution of a statistic. The shape of the distribution of many statistics is either a normal distribution or a t-distribution, and if it's not, we might force it to be on a normal distribution. The mean of the distribution of a statistic turns out to always be the true value of the statistic in the larger population. The standard error differs depending on what type of statistic you have. There are many different types of standard errors, but it's always inversely related to sample size. We saw 3 examples in this module: the standard error of the mean, the standard error of the correlation coefficient, and the standard error of an odds ratio. All of those had sample size in the denominator. So the bigger the sample size, the lower the standard error. But notice there's many different standard errors. Let me just repeat that. There's many different standard errors. A lot of people think that this one, because this is the one they most commonly see, the standard error of the mean, is the only way to calculate standard error. Well, no, that's the standard error of the mean. Every other statistic has its own formula for standard error. But notice they're all related to sample size.